So, hello all. Good evening. It's already 6 p.m., but I'm afraid nobody has yet joined the class. So, I'll wait for another 5 minutes maybe and wait to see if anybody joins. Then I'll continue with the class. Uh, Good evening, Mr. Pravakar. So, you are the first one to join today. So, maybe we can start the class with you itself and others will join. So,
Sure, sure.
so actually, I had a few things to discuss today. So at the start, usually I give my introduction, but I hope that my introduction is well known to the audience, whoever is seeing through this through YouTube or whoever is joining. So, welcome to all. Thank you, Mr. Prabhakar, for diligently joining in every class. And let's start with the today's agenda, maybe. So, for today, I have three things in mind. One was that last week you had told uh, to me to discuss the week two assignment problem for the current curriculum. So that is one thing. Another thing is week three previous year's assignment problem is still pending, and then through the email request, I will also discuss about the partitioning in the stiffness matrix and interchange of the rows and columns to bring the known
Yeah,
and
what is the basically what is
Mhm.
the easy method to put a joint number so that there won't be any issue with the final matrix. Also, if there
Okay.
is any changes in the order of the displacement, how to regroup that matrix. So I
Mm-hmm.
got some
Yes, yes,
confusion.
yes. So I'll discuss the actually in the week four problems. I guess at least in the previous year, I saw there was a big problem given which you need to solve, and there are many questions related to that. So I will discuss one big problem today, where we will also face those issues. So we'll solve them together, and so we know the solution. And also in the end, I will tell you what is the easy way to do the joint numbering so that you don't have to interchange the rows and columns. So with that, so let us start with the very quickly with the week 2 assignment problem for the current curriculum. So I would like to ask, do you have this document, the assignment solution of week 2, which is open currently?
Sorry, yes, I saw that in the net. Yes, it's
Yeah, yeah.
available in that.
Yes, yes. So after means on this, do you have any further questions? Like,
Now,
is
this question number one is okay. That is a the stop deflection method. No issues on that. Yes, this couple
okay.
of questions I had some problem
Yes, yes,
issues.
yes. Okay, then what we can do is like we can quickly discuss, and whichever question you have the problem, we'll discuss that in detail. Okay. So,
Okay, fine. I don't
uh,
remember exactly, but anyway, let's go
yeah,
through
yeah,
one by
yeah.
one.
I
Then
will I
I'll.
will scroll through all the questions. Don't
Yes,
worry.
yes.
So first question is slope displacement method. Under which category does it fall? Obviously, displacement method of structural analysis.
Displacement.
So that is correct. Now determine the degree of static and kinematic indeterminacy. So kinematic indeterminacy here is 0. Static
Mm-hmm.
indeterminacy is 3 because like the load is not drawn over this beam, right? So we don't know whether
Correct.
the horizontal force will act or not. So we have to consider
Correct.
all the degrees of freedom. So 3 degrees of freedom here, 3 degrees of freedom here, and 3 equations of equilibrium. So the correct answer is 3. 3
Yep.
and kinematic indeterminacy is 0. So this is fine. Next, how many degrees of freedom should be removed from the given beam to solve it in displacement method? So there are no free degrees of freedom. So option C, is it fine?
Yes. No. What is that question? How many
Yeah,
degrees of freedom should be removed from the given bit to solve it in? Okay.
displacement
Displace.
method. Yeah,
Okay. Since the displacement method, all the
all the displacements are known.
kinematic interface is zero. Okay.
Yeah,
Yeah.
yeah. So it is answer is 0.
Probably
Uh,
I've given that none of them. I was thinking a three or something in that equation. Probably I might have given the wrong answer there. Yeah.
Oh, okay, okay. So I hope now it is clear. Now,
Yep.
in the given propped cantilever beam, the support
This
A
is clear.
is fixed.
This is clear.
This is clear,
3.12
right? Yeah.
Yeah.
So in this question, I I sort of had a small addition in the solution that is given. That is absolutely fine. That is the solution from the moment area theorem, how to calculate
Yes.
displacement. But there is a quick solution to this.
Or
Is
even if you pull out a standard prop cantilever equations, you find that
Yes,
reacts.
yes,
So
yes.
that is
So if there is a load here called P, then what is the displacement here? That is our interest. So usually we know the load at the end of the cantilever, not at the mid
mm,
span. So in this case, what we have to do is, say the beam is bending like this, and after
mm,
this it has actually goes straight because there is no loading in this part of the beam,
exact.
right? So we know this one. How much is this one? This one is PL cube by 3 EI.
Correct.
And we know the extra part. How much is this? This is actually slope multiplied by the this distance.
Length, distance.
Yeah,
Yes.
L by 2. So it is PL square by 2 EI multiplied by the length by 2. So this is how you calculate the total distance at the end, and then you just equate both the distances from the two solution. So
Clear.
I hope
Clear.
this is clear. The answer is 5.25. Oh, sorry, 3.125. Okay, fine. So next is, what is the size of the stiffness matrix for the given
Six
beam?
by six by six by six.
Yeah,
Three
6
six
by
and one
6.
three.
Yeah. So 6 degrees of freedom are already drawn in this problem, so no worries at all. So next is, find whether the truss is stable or not. So in this case,
Yeah. Why it is unstable?
yeah, it is unstable because the m plus r is actually less than 2j. So this is actually a roller support, I feel. I guess this one is a little bit confusing. So
Yeah, because I thought it is one is spin and one is roller.
yeah, okay. If you know that, like, this is hinged and this is roller, so then we
Hmm.
can find what is the number of members and joints. So how many joints? One, two, three, four, 5, 6, 7, 8. So there are
Hmm.
joint equals to 8. Members, how many members? 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 members, and their unknown reactions are equals to 3 because one is hinged, 2 here,
Hmm.
and 1 here.
Hmm. Hmm.
So m plus r minus 2j is actually minus 1, right? So
Okay.
hence it is unstable actually.
How, I mean, physically, if you see that, how, I mean, it won't,
Physical.
visual inspection, if you see that,
Yes.
all or it is a triangular.
Yes,
Okay. There
yes.
is nothing called, I mean, all members are got a triangulation.
Okay.
And one is
So,
fixed and one is roller.
hmm, hmm, hmm.
I mean,
So,
how it becomes
yeah,
unstable.
yeah, yeah. So, actually, what is happening here is, if you can, first of all, if it is like m plus r minus 2j, if it is negative, then obviously it is suggesting that there is less redundancy. That is, this structure has to be unstable. And if we want to
Hmm.
see it physically, is that if we give a kind of load here, as far as I can visualize, let's draw this in red color. Sorry. So say if we load it like this here, so there is a chance that this will just bend on this hinge kind of thing. I hope I am able to explain it a little bit like this, because there is very less redundancy in this part. So if there was one member like this, then this would like
No, no, no.
hold the truss together.
Agreed.
Yeah.
But the thing is, what are that bending pattern you are written?
Mm-hmm.
Okay.
Mm-hmm.
That member 8 and 9 will
Yes.
definitely will have that sufficient stiffness to hold it back there. Correct?
uh
Because there is a triangulation.
mm,
I'm just arguing. I mean, I'm
yeah,
just
yeah, yeah,
I
no,
mean,
no issues, like, let me also visualize. mm,
because if any member wants
Okay.
to deform, other member will give that a stiffness, axial stiffness for that.
Okay. Mm,
To be honest, when I answered it, I didn't go through this equation M plus R, but just I saw that it is a full complete triangle and one hinge and one roller. I thought it is stable. So
no, no, no.
I didn't check that equation. To be honest with you, I
Yeah,
didn't
yeah,
check
yeah.
that equation.
Yeah, yeah, yeah. No, from equation we are already getting that it is unstable, but visualizing
Right,
it
as per
sometimes,
equation, it is fine. Yes,
yeah,
yeah.
sometimes it may be difficult to visualize also.
Okay.
Um, Let me think how to. But to my understanding, I feel this is not like stable because there are four joints here
But
and.
anyway, equation suggests that it is unstable. As I said, it is. To be honest, I
Yeah,
didn't check that equation. By looking into that, I said, I mean,
yeah,
I
yeah,
just
yeah,
put that it is
yeah, yeah, yeah. I
stable.
understand. Yeah, but like to my understanding, I think there is one more member at the middle here needed to hold
That
it
gives more
together.
stability. More stability, yes, I
Yeah.
agree with you.
Hmm.
But question is it really? But anyway, let us think. Okay, fine.
Yeah, yeah, yeah. Okay. Hmm. So now the next question is, which figure shall we use to determine the elements of the second column corresponds to degree of freedom number 2 as shown in the
Correct.
flexibility matrix. So option C, there is I think no doubt. The 2
Why
is
it is option? Why not option D? It is a
uh,
point load.
mm-hmm. No, so actually this is the deflection. This is not the
Is it
moment diagram.
deflection or bending? Okay, probably
Yeah.
I got missed out. Yes. Okay.
This is the deflection. So when we actually are talking about the degrees of freedom
Okay, fine. Got
in
it. It's
kinematic
my
degrees
mistake.
of
Yeah.
freedom, it is
I
actually the
got
deflection.
confused with the bending moment diagram. Then probably I
Yeah,
put that
yeah,
D.
yeah.
Okay, fine.
Okay, I
Oh, it's a
hope it is.
deflected diagram. Always it is a deflected diagram. What we
Always it is the
consider.
deflection diagram. Yeah, yeah.
Okay,
Correct.
displays. Okay, got it. Yep,
Okay.
clear.
So suppose a structure has static indeterminacy 4 and kinematic indeterminacy 5. So how many redundants considered for force method? So for force method it is the static indeterminacy number of unknown forces. So it's
Mhm.
4. The static indeterminacy, right? Fine.
Yeah, number of equations required. I mean, number of it. Okay, fine.
Yeah. For
Yep,
force
clear,
method
clear.
it's the static indeterminacy. For displacement method is the kinematic indeterminacy. So then, in the given stiffness matrix, which column corresponds to the degree of freedom 2?
Yeah,
So,
second column, of course.
second column, of course, yeah.
Yeah.
So that is correct. And this was the last problem. What will be the equivalent joint load for point joint B at the given beam? So this I guess we had discussed in the earlier class. The
Yes, yes.
equivalent load is.
I think I given it in opposite direction. So in the answer,
Oh,
so
okay, okay,
clear.
okay. So this, sorry, not PL by 2. It would be WL by 2 and WL square by 12, right? So
Yeah,
this is fine.
yeah,
So I guess we can wrap up the week 2 assignment here and we can move
yes,
forward
yes.
in class. Okay. Yeah. So before I continue further, I can see Mr. Sudhakaran has joined the meeting. So, to the best of my recognition, I don't think you have joined any earlier meeting. So, can you please introduce yourself to the audience here?
Yes, sir. I'm
Yeah.
Sudhakaran.
Yeah.
Now I'm currently pursuing my Master of Structural Engineering at Alagappa Chettiya Government College of Engineering, Karaikudi.
Okay. Okay.
Regarding this, I am interested in a research field and also a teaching field. So this is the first time which I
Yeah.
uh, registered for the NPTEL course. Already I completed the concrete technology course,
Mm-hmm.
second structural engineering in mathematics. That
Okay. Okay.
and this topic is previous to my first semester in one unit,
Okay. Okay.
so I kindly registered this class.
Yeah. So,
This
I couldn't hear very nicely, but I feel that you are a student of structural engineering, master's degree.
yes, yes, sir.
Okay. Okay. And in the
second year
department of civil engineering?
in a department of civil engineering. In
Hmm.
my major is structural engineering.
Structural engineering. Okay, okay, okay. Very nice. So maybe like many of the things that will be a certain revision for you, because almost many things you have already done. So any specific expectations you have from this live session, live interactive session?
This is a first time. If any doubt means I kindly ask to you.
Okay. Yes. 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 Sure. So, okay. So, I would like to introduce myself to you. I am Sharanya Banerjee. I am currently a doctoral student in IIT Delhi, Prime Minister's Research Fellow, and these are my contact details. You can anytime, if you have any doubt regarding this course, you can email me in this email ID. My personal email ID is here, and my
Yes,
institute
sir.
email ID is also given here. This is my website, which you can find from the, I guess, the Excel sheet. I don't know, you can check. And
Okay, sir.
brief introduction about myself is, I am currently doing my doctoral degree in IIT Delhi under the supervision of Professor Vasant Matsagar and Professor Deepti Ranjan Sahu. And also, I am currently staying in Toyohashi City in Japan for a research stay for 6 months, where I am doing some collaborative research between Professor Vasant Matsagar, Professor Taiki Saito, and myself. So this is a part of a fellowship that I have received, a Suzuki Foundation Fellowship from Japan, which has given me the opportunity to come here in Japan and do research here. And you can also see my publications. You can see my research area is actually on structural dynamics on the vibration control devices, which is very different from this course. However, the matrix method in structural analysis is a very important course, which you all always have to like be very fluent in, right? So without so if you don't have any further questions, I'll move ahead with the class.
Having a further routine use recent days, IIT Bombay has been entered for the research internship opportunities.
Okay.
In this regard, I have a doubt about structural dynamics,
Oh, okay. Mm-hmm.
whether I am clarified this doubt personally on now itself or
Okay, so what can be done is, let us keep that for the end of the class. So in the end of the
okay.
class, we can discuss that further. Okay.
Okay. Thank you for your opportunity.
Okay, okay, sure, no problem. And the like common methodology which we follow in this class is that this will be a very interactive class where I'll be taking on some of the previous year's problems. I'll be solving them, and more than that, I'll be asking what you want to learn from this class. Like, do you have any specific queries? Like, currently, the first 15 minutes of the class, I discussed about the week 2 current assignment problems, right? So that is not a part of like what was planned for this class, but because it was asked by the audience, I will explain that, something like that. So anything, if you want to know, you can ask and we can discuss about that. Okay. And
Okay.
yeah. And so right now we have two things in our hand, which we have to do. One is the week 3 assignment problems, and another one is the week 4 assignment problem, specifically with importance to the uh, some of the methods which were used there. So first, I would like to quickly finish off the week 3 assignment problems, because if I delay this today, I know that I will finish the class with week 4 assignment problems only, and then this will be pending till week 5. So I'll quickly discuss this. I hope this is acceptable to the audience, right? So yeah. So in week 3 assignment problem, the first question was, a matrix suppose A is a matrix and its symmetric and antisymmetric parts are S and U respectively. So what will be the product of U and S? uh, that is US. So does the class have any problem with this question? If not, then I will try to like not solve everything in this class because we don't have so much time. So I would just explain the method how to do this. So we know, if we have a matrix A and we can do this. So this is basically A, right? Matrix A. I hope my screen is properly visible to all. So matrix A can be broken down like this, right? Half
Yes.
into
Yes.
A plus A transpose plus half into A minus A transpose. So this will be a symmetric and this will be an antisymmetric matrix, right? So this is S, this is U. You can find these two matrices and then you can multiply US and you will find the answer. The answer to this question is, I think, number 3. So I am not solving it the entirely in this class because we don't have time. So next is, suppose A is an orthogonal matrix and B is the inverse of A. Then what will be the value of A transpose? So what will be the answer?
Is it B?
Like A transpose equals to B, you are saying, or option B?
Yes. Yes. Yes.
Yeah, yeah.
A trans
Yeah, A
is equal to.
transpose will be B because for orthogonal matrix A transpose equals to A inverse, right? And A inverse is B. So this is the correct answer. Then what will be the inverse of the following matrix A? Again, I seriously doubt whether I would like to solve it here right now and use this time. So I'll just give you the answer. I hope you can solve this question very easily by yourselves, right? So the answer to this question would be option B. Okay. So actually, I had planned to solve every of these questions in the last class, but many more important discussions come up, so we cannot take this small calculation part in the class. So, anyways, so but we will discuss the conceptual portions of all the questions very thoroughly in this class. Be assured. So the next question is, if A if the matrix A is a 5 cross 5 matrix and B is also a 5 cross 5 matrix obtained by multiplying each element of A by a scalar k. So we know B is k times A. Then which of the following is true? Determinant of B equals to which is the correct answer? It's a 5 cross 5
B.
matrix.
KX5 was determinant
K to the power 5, right? Determinant
It
of B
is.
will.
Yeah. It is the k to the power of 5 into determinant. Yeah. Yes.
Yes. So this is the correct answer, and uh, and of course I think you know that if you have any doubts, if you feel that the class is moving fast, you can stop me there and you can ask me, right? No hesitations. So what will be the upper triangular matrix of the following matrix A? So how to find upper triangular matrices? So we have A like this, 1 2 1 2 3 2 1 3 2. So let's call this row 1, row 2, row 3. How to find upper triangular matrices? So we can simply see that this first element becomes 0 and these two elements become 0. So how to ensure that? We have to transform A. First we have to do. So how will this second row first element be 0? If we subtract
2
the
minus
first row,
R1.
yeah,
R2 minus 2 R1.
R2 minus 2 R1, that will be our first step, and our second step would be R3, uh, R3 minus first R1. So this will give the first element 0. So this will be a second step. So from our first step, this will be 0. From our second step, this will be 0. We also need to make this one 0, right? So after the second step, what will be the value of this element, the second element of third row? It will be, when we do R3 minus R1, so it will be 1 minus 1 0, 3 minus 2, this will be remaining as 1, right? And this will be 2 minus 1 1 as well. So now and what will be the value of the second row after the first assignment? So it will be R2 minus 2 R1, so this will be 0, this will be 0, and 3 minus 2 3 minus 2
It will
into
be
2,
minus 1.
this
It
will
will
be
be minus
minus
1.
1, right? And this, let's forget about this. So the third step would be that you can just make this 0 by adding this with R2. So R3 plus R2. Okay. So by doing these three steps, I guess you can already find what will be the upper triangular matrix. So what is the answer for this question? Although like we have already found the answer quite close, we're quite close to the answer, but still I'll tell you the final answer. So the final answer is this. Our prediction was correct. This is minus 1 and this is 0. Okay. So the final answer is this. I hope there is no confusion in this question, right? So moving forward, is that fine? I hope that is fine. So then use the result of question number 5 to solve the equation ax equals to b. So this is a, and we have to solve ax equals to b. So b is this. So how do you solve this? So if we have
The option 1
ax
is the answer.
equals to b, answer is I'll have to check.
Okay, fine.
No, I'll just check it quickly. Answer is option 2 actually. So I think you have to solve this. It is not like very quick answer. So first what we have to do is we have transformed this A to something else, right? A with upper triangular matrix A, right? And this is the same. So the same transformation has to be done in this B matrix also. Okay. So in the B matrix also we have to find that what is happening. So R1 is remaining R. So if we see what is the B matrix, R1 is remaining R1, so that would be 7. R2 is becoming minus 2 R1. So R2 minus 2 R1 would be minus 4, right? And R3 is becoming R3 minus R1, so this will be minus 5. And then R1 R3 plus R2, so minus 5 plus plus minus 4, so it will be minus 9. I'll just check whether this is correct. This is minus, sorry, this is minus 9. Because this is 5 minus 2 into 7, so 5 minus 14, this will be minus 9. And then what will be this R3 minus R3 minus R1 was first of all 2 minus 7, that is minus 5, then minus 9, minus 5 minus 9, this will be minus 14. So this will be the transformed B matrix. So when we have the transformed B matrix, we have to write the equation like this. So what was the answer for this? 1 2 1, 1 2 1, 0 minus 1, 0 0 0 1. This was the answer for A. We have x1 x2 x3, and we have 7 minus 9 minus 14. So from here we know that x2 equals to 9, x3 equals to minus 14, and x1 we have to solve, but there is only one option with 9 and minus 14. This is this answer. So the correct answer is 2. So
Some doubt, Mr. Benny. What is that?
yes,
See,
yeah.
upper triangular matrix. Okay, this final equation is okay with me. 1 to 1,
Okay.
that is that what we got it.
Mm-hmm.
Then your x1, x2, x3 is the variables.
Yes.
Okay,
Hmm.
that should be is equal to 752, right? Why you taken 7? It should
Oh,
be equal to
no, no.
ax is equal to b, right? 752.
Yeah, ax equals to b, but your a was this. A is this one. A is not the upper triangular matrix.
Okay, okay. Then you had to, along with that b, we had to convert. Okay, got it, got it,
Yes,
got it.
yes. Yeah.
Along with that b, we had to convert. Along with that triangulation, when you are doing
Yes,
the
yes,
triangulation, we had to convert. Okay, got it,
yes.
got it. Thanks.
So when you convert this a to upper triangular a, you have to also convert this b to the equivalent of
Agreed,
that. Yes,
agreed.
yes. So I hope this is clear. The answer is also clear. We have almost solved this here. So next is any matrix A can be decomposed into LDU form. What will be the LD matrices, L and D matrices for the following matrix A? So this is a very interesting question. So they are saying that this matrix A should be transformed to L, D and U. So what is L? L is the lower triangular matrix. U is the upper triangular matrix and D is a diagonal matrix, right? So how do you convert this? How do you make this transformation? Any inputs from the class? Any ideas?
Now, first we have to convert, right? Lower
Yeah.
triangle and upper triangulation.
Uh, okay. So you can yes. So actually, in the class also there was something like this discussed in the video lectures. So uh, okay. Now let me go on one more step with this. So say this is matrix A. What does L matrix mean? This will be 1 0 0 1 0 1, right? This is fine, right? let
Yes, yes.
let us assume this is L21, L31, L32. This is the L matrix. And then what is the D matrix? Say this is D1 0 0 0 D2 0 0 D3 0. Okay. So what is U matrix? U matrix is 1 0 1 0 0 1. And here let us assume U12, U13, U23. Okay. So first let's keep this L as L and let's multiply this D and U. Okay. So what do we get? We get L like this, and if we multiply D and U, what do we get? So if we multiply D and U, first element is D1, no doubt. Multiply this first row with the first column, first element is D1. Second element is first row with second column, D1 U12. Third element is D1 U13 plus 0. Yes, that is the first row. Then second row, let us see what is the second row. Second row, first element is this multiplied by this, so 0. Second element is this multiplied by this, so only D2 here. Third element is this. Okay, so I am doing this, but I guess you are not able to see what I am saying this. So anyways, I will not say this again. I will say second row multiplied by third column. So second row multiplied by third column, what is the answer? It will be uh,
D2 U23.
D2 U23. Yeah, correct. So then third row multiplied by first column is 0. Third row multiplied by second column. Oh, I have done a mistake here. This is actually 0. This is D3. I hope you all know that correctly. But anyways,
Yeah.
so this is D3. So third row multiplied by second column is also 0. Third row multiplied by third column would be D3. Okay. So we have got one L matrix and one another matrix. Let us call this, say, U dash. Maybe U dash is okay. So if we transform a matrix, say A, into lower triangular like this, and another U dash, where we have the diagonal elements not as 1 but something else. So this LU decomposition you have already done in class, right? And you know this is the formula for the LU decomposition. Do you remember? This was discussed in the week's
Yes,
lecture
yes,
videos.
yes,
So you
yes.
already have the formula for each element, and this is the by using the formula, but I will never suggest that you remember all the formula. Simply you can also multiply L with D, and you can find each element here. It's not a very difficult task, I guess. If you don't want to remember the formula like me, if you want to remember the formula, that's like well and good, you can just easily find out. So the answer for this question would be, let me check, the answer will be option 1. This is L, this is D. Okay, so I hope you can solve the rest part of this problem. Almost everything is solved, only you have to put it in this formula, right? So any queries for this question? No.
No, no.
Okay, so moving on. Yeah. So okay, um, so next question is, which one of the following is not the property of a positive definite matrix A? First option is the diagonal elements are always greater than 0. Second option is all the eigenvalues are greater than 0. Third option is all upper left submatrix will have positive determinant. Fourth option is for non-zero vector phi, phi transpose A phi should be greater than equal to 0. What is the correct answer?
Really, it's difficult for me. I can't
Uh-huh.
understand.
So so let's rule out, and then we'll find out why the other one is the correct answer. First option is diagonal elements are always greater than 0. Has to be. For a positive definite matrix, diagonal elements have to be greater than 0. Okay, so the determinants also have to be greater than 0. So all eigenvalues are greater than 0. This also has to be. All up.
Mr. Banerjee, I got one
Yes.
more doubt, probably in this class or next class.
Yes, yes.
Oh, why do we call this as a eigenvalues? Because this term I'll be repeatedly hearing it in even the dynamics or when we do the
Yes.
response spectrum or what is that exact meaning? What is that? Is it related to something in the matrix, that eigenvalues, or what physically it means?
Oh.
Because when we call the in the response spectrum also, when we
Mm-hmm.
take this mass participation or the vibration, there also some term very
Mm.
often we refer it as eigenvalues or something like that.
Yes,
So
yes.
what exactly it is a physical
So,
interpretation or meaning of that? What it is?
yes, okay.
If you
So
want to take it in the next class, it is fine.
yeah, we'll discuss this in the next class. So eigenvalue basically is a like kind of feature of a matrix, and the exact physical significance I can discuss in detail in next class. However, I don't know whether you remember, the eigenvalue analysis actually gives us the natural frequency of the system, in dynamics, in structural
Yes,
dynamics.
they're for different modes. For different modes.
Yeah, for different modes. Yes, yes. So the I will get back to you with the physical significance. I am not sure whether any kind of eigenvalues for any matrix will have some physical significance. I am not sure about that, But for a very specific kind of matrices like the stiffness matrix, which is always positive definite, and it is banded at the diagonal region, then the mass matrix, these kind of matrices, when they are put together, the eigenvalue analysis always have some physical significance of what are the different
In
modes
particular
of.
to this matrix, what is that eigenvalue means in the matrix? Even that also I'm not clear on that.
Okay. So when we do eigenvalue is say like okay, so you have a matrix like this, say A. If you
You can take the example of the question number 9, that matrix. You got 1, 2, 3, 5, 3, 2, 7, 7, 8 in that question number 9.
okay, yes,
This is
yes,
something, yeah.
okay. So I'll just write it here. So you have a matrix. First, let me write it in the kind of uh, what to say, the notation form. Then we'll go there. So there is this part. So this is called the characteristic equation of a system. I don't know the exact terminologies of this. I'll get back with this in the next class, properly prepared. But however, this is the characteristic equation of a system. Let's ignore the right hand side part. Let's make it 0. This is actually the characteristic equation of a system. Okay, so these are the like different eigenvectors of the system, and this lambda is gives you the different eigenvalues of the system. So how does here A is any matrix, I is the identity matrix, and X is the eigenvector of the system. Okay, so in terms of dynamics, what does it mean is that you have a stiffness matrix K, you have some natural frequency of the system omega square, and you have the mass matrix M. So mass matrix actually is a kind of only diagonal matrix. Okay, so when you you can like easily divide the mass to make it, let's say, K by M, and you can make this identity matrix. The form is very similar to this first equation. So this kind of equation, this is called the characteristic equation of the structural system here, of any structure. Say you have a multi-story building and you want to do some dynamic analysis. You have its stiffness matrix K and you have the mass matrix M. So this is kind of the characteristic equation of this structural system. And in this specific equation, the omega square value will give you the natural frequencies of the structure, and the x values will give you the mode shapes of the structure. So you will get this is the building, so you will get different kind of mode shapes of the building. My drawing is very bad. So let us consider the building as a single line. So you'll get different kinds of mode shapes of the building like this. Like this. Okay, so these each mode shape will be corresponding to certain omega values. Okay, and this is like this will depend on the size of the K matrix. So if it is say 3 cross 3, then you will have 3 mode shapes and 3 omega values. If it is n cross n, you will have n mode shapes and n omega values. So this is how we do eigenvalue analysis in structural dynamics. But here, without any information on the matrix, eigenvalue actually means this solving this characteristic equation. This one, A minus lambda identity matrix equals
And it's
to,
related to some linear equations.
yeah, this is
It
linear
is not
equation.
related to any single given matrix, but it is a system of linear equations where we need to find those eigenvalues. What you're
Yes,
saying.
so here the lambda is the eigenvalue and this x is the eigenvector of the system. Okay, so So if these eigenvalues are always greater than 0, that is the requirement for the positive definite matrix. These eigenvalues will always have to be greater than 0. Okay. So this is some feature of the positive definite matrix. Fine. And I will discuss in detail. Okay, let me write it down. I will discuss in detail like significance of eigenvalues and these things in the next class. Okay, very good. So the more we get questions like this, I feel very good. Like we can discuss something more in this class, apart from the uh, normal assignment problems. So moving on. So the third option is all the upper left submatrix will have positive determinant. Yes, this has to be true. And the last option, this is actually false. So this is the correct option for the answer, and this is for any non-zero vector phi transpose a phi has to be greater than equals to 0. So this is wrong. This phi transpose a phi has to be always greater than 0, not greater than equals to 0. So this is where the catch was, and this is the correct answer. Okay. So this is something related to the theory behind positive definite matrices. This is not like anything which you can directly correlate and like find. You have to remember what is positive definite matrices, then you can answer this question. So the next question is, what will be the rank of the following matrix? uh, how to find rank of matrices? Any suggestions? Yes.
No, really, no.
No.
This.
Okay. So the simplest way to find rank of the matrix, which I feel, is like you try to make the matrix a upper triangular matrix. Okay. So when you are trying to make it an upper triangular matrix, so first row remains the same, 1 2 3. Second row, what you are basically doing here is R2 minus 5R1. Okay. So second row becomes uh, 0, then minus 7. Please also do it with me. I can do mistakes and you can correct me. Minus 13. Please check whether R2 minus 5R1 will give us this one. And also in the same matrix, let us do R3 minus 7R1. Okay. So again, this is 0. R3 minus 7R1. 7 minus 14 will give us minus 7. R3 minus 7R1. 8 minus 21 would give us
Minus
minus
13.
13.
Minus 13, yes.
Okay. So without going any step further, we can say that these two rows are actually the same. So no different information is obtained from these two rows. So the rank of this matrix will be 2. Okay. So am I clear? Yeah. I hope there is no other doubt.
Yes,
So
yes.
if you just go on for the third step, you will just do R3 minus R2 and your last row will become 0. So 1 is a 0 row, which means the rank will be 2. Okay, that is correct. Now what is the last question we have here? Rank of the matrix is done. Okay. Last question is, matrix A is carried out Cholesky factorization. A equals to L transpose. What will be the value of L33? So again, for this you have ready-made solution here given in your lecture class, how to find L1, L21, L31, all these things. So you can directly use these formula to find the answer, or if like myself, I am not good with formula, so what I'll do is I'll just write down this equation. I'll write like this: L11 0 0, L21 L22 0, L23, L32, L33, and what is L transpose? L11, L21, L31, then mm, 0, L22, L32, then 0, 0, L33, and you multiply both to get the answer. Very quickly you can check. First column, first element of this will be L11 square, right? So the first formula is L11 equals to root A11, root A11. Okay, so like this you can actually derive the formula and you can find the answer. Otherwise you can use the formula. So I hope there is no problem with this assignment now. All the things are cleared up.
Yes, yes.
Okay, so let's finish it here. Now let's move on. So now we are not pending with any of the previous assignments. We can move on to this week's assignment. Very good, well and good. So in this week's assignment I will first discuss I will discuss the assignment problem of previous years, and through that I will try to explain the different questions that you had raised earlier. So there is something in the chat box, let me just check. Please share the previous solutions also. I joined late for this problem, sir. Oh, okay. Yes. So there is a new member in our audience. Can you kindly introduce yourself, Jashwant, if I am not wrong?
Hello, sir. Good evening.
Yeah.
Myself, my name is Swan
Yes.
from
Yes.
Mysore.
Okay. So.
This is the first time taking this NPTEL courses. I was
Mm-hmm.
not aware how it goes and all these things.
Mm-hmm.
So actually, I read the email yesterday. So
Okay.
I'm. This is the first class I'm attending the problem solving session.
Yeah, no problem. You are welcome to our class. And so what basically we do here is that we solve some of the previous year's problems in this class, so that you can get help to solve the current assignment problems. And also through those problems various doubts come up, various questions come up, which we discuss maybe in that class, maybe in next class, sometimes in very much detail, sometimes in lesser detail. So it is, everything is under our control, everything is as per the requirement of the audience. Nothing is like nothing is fixed in this class. So what I would request you is, like, you join the class and you bring in your expectations, your suggestions, that what should we discuss in the next class and where you are facing some problems, and we will actually take up those things and discuss it further. And regarding the previous solutions, so this is the fourth week of the class. This class is already available in YouTube for all the first three lecture classes, and this one, the class that is going on right now, that is also being recorded and that will be uploaded to YouTube. So you can go back to YouTube and see whatever missed lecture part you have missed. And also the different documents, the different writings, the different notes that I am preparing here, I will upload this to a Google Drive link, which is also shared with you. You can go through the Google Drive link to find the previous question answers. Okay, I hope that clears
Thank,
your doubt.
thank you, sir.
Yeah.
Thank you, sir.
Okay, and can you also say, like, what is your expectation from these live interactive sessions? Like, do you have anything specific in your mind?
No, sir. Actually, the class is going on very good. You're solving the questions on to the point, and you're discussing the content as per the requirements of the assignments.
Okay.
So this is going good, sir.
Okay. Then if everything is fine, then it's good. And you can always stop me whenever, if you feel that if you have any doubt, you can like, no need to write it anything in the chat. You can just directly interrupt me in the class, and I will discuss that in
Okay.
further detail. Okay. And
Okay, sir. Thank you, sir.
so yeah, no problem. So let's move on. So coming to our main agenda of today's class, almost 1 hour down. So no problem, like, we have time. 1 hour is a lot of time. So uh, So the first question for the week 4 assignment, previous year's assignment problem is, what is the physical meaning of a stiffness matrix to be singular?
Mr. Banerjee, only one.
Yeah.
What is the date? 22nd August 2023. Today's date, or we are
Yeah.
putting the question paper
Ah,
date week 4.
yeah, this is today's date. This is as per our means my
Okay,
notes.
okay.
Like, this is not the actual. Uh, this is not the actual assignment. This is a document created by me. It's not given in your NPTEL course. Okay, so this is not the current year assignment problem. This is the previous year's assignment problem, and everything is blank in this problem. So don't worry. So, anyways, so so first question is like, what is the physical meaning of a stiffness matrix to be singular? So I hope this is quite acquainted to y'all. I will request for answers here.
Option C.
Option C, unconstrained degrees of freedom. Yeah, absolutely correct. So if so when we find the stiffness matrix, say, of a beam element or a truss element, so right now you are only worried about the truss element, right? So you have the different 2 degrees of freedom of the truss element, and you have the different 4 cross 4 stiffness matrix of one truss element. And if we don't have any constraint to the degrees of freedom, so our stiffness matrix will remain 4 cross 4, and it will be singular in nature, because if we give any force to this member, it will just move with the force. There is no restraint on the degrees of freedom. It will have rigid body motion. So there will be no solution of the equations of motion. There will be no solution of the compatibility equation, say P equals to KU, because this K is actually singular in nature when it is not constrained. Okay. Yeah, pardon? Yes. Uh, can you please repeat what you asked? Okay, no problem. Maybe then that was by mistake also. So now the main question of the night, like, um, answer the following questions for the given truss. For this given truss, we'll solve various questions. I have not jotted down the questions that we want to solve. The reason for that is, like, we will solve the whole truss problem together, and uh, like, we will not try to find any single answer. On the way of solving the whole truss problem, we'll get all the different answers for the assignment. Okay, so I have not written any of the assignment questions here, but we'll solve it together one by one. So first, before starting, can I ask, like, do you have any pen and paper in front of you? Are you solving these questions with me?
Yes, yes.
Okay, so in that case, like, we can solve it together, and the answers that you guys will be telling me, I'll just write the answers down. So before writing the answers down, let's first discuss about the um, different the underlying formulas and the underlying concepts behind this problem. So your whole week 4 lecture videos was revolving around the stiffness matrix uh, of truss elements, right? Stiffness matrix of truss elements. So here is one example truss problem which we'll solve using all those formulations and concepts. Okay. First of all, we have one hinge support. So 2 reactions here. Okay, let me use red color. 2 reactions here, 1 reaction here, 1 reaction here. Okay, very fine. So can you say what is the degree of static indeterminacy and kinematic indeterminacy of this truss?
Static indeterminacy 1.
1, yes, correct. Like, let's solve it. How we get 1? M plus R minus 2J. How many members? So let us also mark the members here. 1, 2, 3, 4, 5. We have 5 members. Reactions we have 4. Joints we have 1, 2, 3, 4. 4 cross 2. So your static indeterminacy is 1, and visibly also the extra support is visible. So this is actually the external indeterminacy, right? There is no internal indeterminacy. Okay, very good. So next question is, what is the kinematic indeterminacy of the truss?
Four, is it roller support? Point C
Yeah,
and B?
this is roller
Okay.
support. Yeah, yeah.
Both
Four,
C and
four,
B.
4 is the correct answer.
Four
We
is the answer.
we have 2 degrees of freedom here, 1 degree of freedom here, 1 degree of freedom here. So kinematic indeterminacy is also 4. So I hope there is no question with the static indeterminacy and kinematic indeterminacy of the structure. And let us also write what are the 4 kinematic indeterminacies. So 3, 4, 5, 7. Okay. Now, so so the thing is, let us be clear with one kind of nomenclature. So when I write 3, 4, 5, 7 like this, so this means the joints. Okay. And if I write 1, 2, 3 like this means the members. Okay. So I'd be using this kind of nomenclature in the following explanations. Okay. So this is done. So now first let's quickly write down the formulas of the different truss problems. So say this is joint I, say this is joint J, say this is I1, this is I2. This nomenclature I have stolen from the lecture videos that you have already seen, because I hope like there should be no confusion regarding that. So this is I1, I2, J1, J2. So can you please tell me what is the transformation matrix? What is the transformation matrix size? It is actually 2 cross 4. Okay. Yes. So what is the transformation matrix?
Cos theta sin theta 0 0
Okay.
0 0 cos theta sin theta.
Yes, excellent. You are absolutely correct. So instead of cos theta sin theta, we are writing lambda x and lambda y. This was the same nomenclature used in the class, so I hope there is no confusion. And since we have now written lambda x, lambda y, we will define what is lambda x, lambda y. Lambda x equals to, as you have already mentioned, cos theta. And what is the value of cos theta here? Okay, I'll write down. You can just check. Xj minus xi by L. So if this length is L. So similarly, lambda y is sine theta. What is the formula of lambda y sine theta?
Yj minus yi by L.
Exactly. Yj minus yi by L. As Professor Amit Shaw has mentioned in his lecture videos, so this kind of nomenclature is important for, say, the computer programming. So your computer, to make the computer understand that what is the theta each and every time it's very difficult. But if you give the computer different points and you say point number 2 minus point number 1, so that is very simple for the computer. Okay, so that is why this is very like easy for the computer to understand. And for us, like when we can visualize things, what does this, where is the theta, like which angle is theta, can you say?
With respect to horizontal.
Yeah, with respect to horizontal, like this is the theta angle. Okay, so here the direction of the arrow is also important. So what is the significance of this theta? This theta is actually at the starting point. Okay, and this theta is moving anti-clockwise. So if you have not understood the significance so far regarding this theta, you will subsequently understand it in throughout this class. Anyways, so this is the formula for the transformation matrix. Now very quickly, let us also kind of solve the, like derive the equations. I guess if we just quickly derive the equations, it will be very easy for us to visualize when we are solving the problem. Okay, although this derivation is done very thoroughly in the lecture videos, but still I would quickly repeat it. So what does this transformation matrix mean? So this transformation matrix actually means you have u1 u2 like this. Okay, am I using u1? So okay, forget about it. So you have, so in the local coordinate system, these are the different displacement of the beam of the, sorry, not beam, of the truss element, right? u1 u2 through its longitudinal axis. There is no displacement in the horizontal and vertical. Okay, so then what we do is we use the transformation matrix to convert this into u1x, u2x, sorry, u1y, u2x, u2y. Okay, so this is the transformation matrix that we are talking about. Fine, so very good. So now also let's now talk about the forces. So here is also one force like this, which is going as say F1. Oh my god. At any time, if you feel that you don't understand anything, please stop. So this F1, F2 are actually in the same direction as U1, U2, but it is not discernible, so I just drawed it by extending it a little bit. Okay, so uh, so now we have the forces F1 and F2, and it will be very interesting to see that F1x, F1y, F2x, F2y is actually nothing but T transpose into F1, F2. Everyone agrees with this? So actually when we break down this F1 and F2 into two parts, F1x and F1y. So first, what will it be? What is T transpose? I guess T transpose everyone agrees with. So it will be like 4 rows and 2 columns. In the first row it will be lambda x and 0. So f1x will be lambda x into f1. Lambda x into f1 means f1 cos theta. F1 cos theta means in this direction. Okay. And then second row f1y, it would be 0 f1 plus lambda y f2. Um so where is the where is the where is the where is the oh, sorry. So it will be let us write t transpose. T transpose equals to lambda x lambda y 0 0 0 0 lambda x lambda y. Okay, into f1 f2. So f1x will now become lambda x into f1. Lambda x into f1 is f1 cos theta. F1y would be lambda y into f1. Lambda y into f1 will be f1 sin theta. Similarly, f2x and f2y. This part is clear. Everybody is happy with whatever is written till now. I hope
Yes.
so. Okay. So now for the simple truss problem in the local axis, what we know, f1 f2 equals to 1 minus 1 minus 1 1 u1 u2. Okay, everybody agrees. Now
Yes.
if we want to convert this into f1x f1y f2x f2y, what would it become? It would become t transpose f1 f2. Fine. Now this f1 f2 we can put over here. So it would be t transpose 1 minus 1 minus 1 1 into u1 u2. Fine. Now what would this be? Okay. Just one thing I have been missing. This is not my fault, everybody misses. AE by L, of course. Okay, this is the stiffness matrix. Okay, T transpose AE by L 1 minus 1 minus 1 1. And what is this U1 U2? This U1 U2 is actually T transpose over here transform into U1x. Oh my god, there is no space. Okay, so we write AE by L here, AE by L here. So now we again write f1x f1y f2x f2y equals to T transpose AE by L 1 minus 1 minus 1 1 T into u1x u1y u2x u2y. This part is clear to everybody?
Yes.
Yes, sir.
Yes. So this part actually now becomes the K stiffness matrix. This is already derived in class very nicely, but still I just recapitulated like how the stiffness matrix is formed. So this K is now what? Nothing but AE by L T transpose 1 minus 1 minus 1 1 into T. And what this will yield? This will yield you the big matrix. Lambda x square, lambda x, lambda y, During my bachelor's, I studied it with L and M denotation. I don't know whether anybody could relate that denotation, but anyways. Y square. So basically, whatever we have in the first two rows, that will just the negative of that will be in the final two rows. I hope these features about the stiffness matrix of the truss is known to you, right? This will be very useful, like to remember. Okay. This is the stiffness matrix of a truss element. Fine till now?
Yes.
Okay. So this was all about. mm this is all from my part in today's class. Now whatever we'll do it together. So now we have this problem. This problem. This problem is clear to us. Let us again and again we have to draw this problem, so it's not required. Let's take this problem. This problem is also there in your notebooks. Let's start deriving what is the stiffness matrices of member 1, 2, 3, 4 and 5. The member denotations I have used, I would request you to use the same denotations. The reason for that is you will just tell me the answer, I'll just write down the answer. Okay. So member 1 is this member AD, member 2 is this one AC, member 3 is CD, member 4 is CB, member 5 is BD. Okay. So now let us start. What is the stiffness matrix for the different members? For member 1. So for member 1, what we want to find out, first of all, let us draw member 1. Why is my straight line so curved? This is member 1. And with the member 1, what I'll also draw is the different degrees of freedom for that member. 1, 2, 3, 4. Okay. And this is all the information that we need. So first I would want the answer of lambda x and lambda y. Please.
What are the dimensions, Mr. Banerjee? I
Uh,
didn't note it down that
Dimensions are this one is 4, uh, this one is 4, this one is 4, this one is 3, this is 5, this is 5. The basic Pythagoras theorem dimensions. For the first member, we are currently looking for lambda x, lambda y.
Lambda x is 4 by 5.
4 by 5, yeah, that is correct. So we can write 0.8. Lambda y
3 by 5.
3 by 5, 0.6. As soon as I get the first answer from the class, I will move on. I hope everybody could follow. So now transformation matrix, please. Lambda x, lambda y, 0, 0, 0, 0, lambda x, lambda y. Okay. So far so good. Stiffness matrix, please. Waiting for the answer.
0.64.
0.64, absolutely correct.
0.48.
0.48.
and minus 0.36.
Yeah. Okay.
64 or 0.36? 0.36.
Uh,
Yeah, lambda x square. Yeah, minus
minus
0.64. Minus
0.48,
point.
right?
Yeah, yeah, clear.
Yes. So yeah. So in the next, I think you are telling about 0.36 in the next one.
Yes, is
Yes.
0.36. Yeah.
Yes. Yeah. So this is the complete information on the stiffness matrix. Now we have to just reverse the uh, values. Take the negative of the first two rows. Just an unfortunate question. Is my handwriting understandable? I hope so. Okay. So this is complete information on member 1. Everybody agrees till this part, right? So why I have written this extra line here, just to remember that we are correlating u1, u2, u3, u4. This is very going to be very important when we are trying to assemble the matrices. 1, 2, 3, 4. These are our degrees of freedom. Let's move ahead. For member 2, what is our member 2? Let's check. Member 2 is this one, AC, connecting 1, 2 and 5, 6. Lambda x, lambda y, please.
1 and 0.
1 and 0, excellent. Transformation matrix. Transformation matrix I can write. Stiffness matrix. This is member 2. Stiffness matrix, I'll be waiting for the answer. Till
1,
then.
0, 0, 0.
Okay, we already have the answer. 1,
1, 0,
0.
minus 1, 0. Minus 1, 0. 1, 0, minus 1.
Okay. Next line.
Yeah, then 0, 0, then 0, 0.
0, 0. Perfect. Yeah, that's correct. That's all the information that I need. Thank you very much. And very importantly, we have to write what are the degrees of freedom that are associated with this. So, very nice. This is F1, F2, F5, F6. Now these F1, F2, F5, F6, these are not the final Fs. These are the forces from these members. So please don't confuse that these are the final Fs. But the displacement, we can write these are the final displacement because displacement will be same for each member. Okay. I hope you got the point what I tried to make now. Yes. If there are no questions, then I will assume that you have got the point. So member 2 is clear. Moving on to member 3 now. Let's see what is member 3. Member 3 is the vertical member. Very interesting. Member 3 is the vertical member here. We have 3 and 4 like this, we have, what is the other one, 5 and 6 like this. Very nice. I expect this to be interesting to you. This is number 3. Then we are waiting for lambda x, lambda y,
This
then
is 0 and 1.
0 and 1. Any other answers?
Lambda x 0, lambda y 1.
Okay. Thank you. I so I want to like write a little bit more, then come to the answer. This is 3, 3, 4, 5, 6, 3, 4, 5, 6. 3, 4, 5, 6, 3, 4, 5, 6. These are the degrees of freedom. Yeah, lambda x and lambda y. Again, can you say?
Lambda x 0, lambda y 1.
Okay. Any other answers? I wrote the 3,
It
4,
is
5,
minus
6
1.
for some reason.
It is minus 1.
Yeah,
Lambda y is minus 1.
lambda y would be minus 1 actually. So the reason is, if I am considering this point to be the first point, so what is our theta? Our theta is, where is that? Our theta is that at the starting point and anti-clockwise. So our theta is this theta. Okay. Our theta is actually 270 degree. So when our theta is 270 degree, cos theta is 0, but sin theta is minus 1. And if we go by the formula, again with the formula also, yj minus yi would be negative, right? So this was the reason I stressed upon the fact of theta and its.
But what happens if I change the starting and end node? Any wrong? Anything wrong?
No, nothing wrong, nothing wrong. That is why I didn't say that your answer was wrong. I just wrote down that what is the
Okay.
nodes that we are taking. So with respect to these nodes, what is the answer? So in if you are taking other starting and end nodes, the stiffness matrix would be different. That's all. Yes. So now the stiffness matrix, please.
This is 0, 0.
0, 0,
First row is complete 0, 0.
0, 0. Very good. Then
0, 1, 0, minus 1.
yes, very nice. So thank you for the stiffness matrix. So minus 1. Yeah,
Now you
that's
have to change
okay.
the sign. You have to change the sign of that large square.
Sorry, sorry, sorry. Yeah, thank you for the correction. Then we have f3, f4, f5, f6 of the third element, u3, u4, u5, u6. Very good. Quickly, member 4. What is member 4? Member 4 is again the horizontal element with 3, 4 and 7, 8.
Can we copy directly member 2 stiffness matrix for this? Or it will be
Member 2 stiffness matrix. Yes, it will be the same. Only the
freedom,
number of
freedom
freedoms
you
will
need
be
to change.
different. Yes, yes, that is correct. So yeah, so you can just tell me what is lambda x and lambda y. Okay. Then let me write it down quickly without asking any further questions. You can just correct me whenever I am wrong. And I hope the same thing you are also doing in your own copies, notebooks, whatever. This part is okay. Moving on. For member 5. The member 5 is this member. Okay. Wow, very nice. 7, 8. This is 3, 4. I did something wrong, I guess. This is not 3, 4. This is 5, 6. Yeah. I did something wrong here. This is 5, 6. Please, if you have also did the same mistake as me, then please correct it. For member 4, this will be 5, 6. Okay. For member 5, this would be 3, 4. I hope you have corrected it. So again here what we want to do is we want to find out the stiffness matrix with respect to 3. Okay, 3, 4, 3, 4, 7, 8. Okay, so can you give me theta x and theta y?
Lambda x is 4 by 5.
Okay,
And lambda is minus 3 by 5.
excellent. Yes, so this part is done. All the element stiffness matrices are formed. Okay, of course, completing this one. Yeah, so this one I am just writing down. Please correct me whenever I am doing some mistake. I hope you have already completed that in your notebooks. Final call for any questions here. Next we'll move on to the bigger part now. U5, U6. No questions? No questions? I hope no questions.
No.
Okay. Now the main thing is assembling the stiffness matrix. And I don't know how I will do that in this tab. So this the final stiffness matrix would be 8 cross 8 stiffness matrix, right? Why 8 cross 8 stiffness matrix? Any answers?
8 freedoms.
8 degrees of freedom. Very nice. Yes. So let me just try.
Sorry to interrupt, sir.
Yes,
In
please.
the degree of kinematic indeterminacy,
Yes,
we can directly apply formula as 3J minus R. Is it right? 3 times of joint minus reactions. 3J minus R.
3j minus r. For
Degree
kinematic
of
indeterminacy.
yes, sir.
Okay. I
Three
That is
am.
times
for
of
space.
joint.
That is for space element, 3J.
Okay,
Space.
okay. Mm, I guess. Okay, for like you were talking about like 3 degrees of freedom in each joint, and thus minus
Yes.
the total number of reactions.
Yes.
Okay.
Yes.
So, but yeah, for truss element it will be 2 degrees of freedom, 2j, and for
2J.
beam element it will be 3 degrees of freedom. Uh,
Yes.
okay. Okay, yeah, yeah, I
So
think you can use it, but I'm not sure whether. Yeah, it should work. 2 degrees of freedom in each node,
oh,
and minus the total number of
yes, sir.
reactions or constraints. By
Minus
reactions,
the
you mean constraint.
yes,
Yeah,
sir. Yes.
yeah, I think that should work. You can also check and verify later. Okay, so the very difficult part here, writing all the degrees of freedom in this space. 1, 2, 3, 4. Wow. 1, 2, 3, 4. Wow, I managed to do that. Okay, very nice. So, who will say the assembled matrix for me? But let me also discuss this. I think this part is important. So, how do you calculate element 1 1 of the global stiffness matrix? Any ideas?
We have to check that member number 1 and member
Yes,
number 2, where we have that joint
exactly.
1,
Huh.
2, 3.
So whenever we have the joint, okay. So whenever we'll check the joint numbers here of every stiffness matrix, okay, and we'll find whether there is 1 1, whether there is 1 1, there is no 1 1, there is 1 1 here, okay. So you are absolutely correct. Member number 2, and there is 1 1 here, okay, absolutely correct. Member number 1. So what do we do next with the members?
We need to add
Okay.
the corresponding elements.
Yes, 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 exactly. We need to add the corresponding elements. Now, also, I have done a blunder here. Can you guys tell what is the blunder by seeing the first stiffness matrix? No. This, compare these two stiffness matrices. One in red with the formula, and the other which we have written. Answer is already I have told the answer.
Is it AE by L?
AE by L, yes, of course. We have forgot to write AE by L. So for the first member, L was 5 meters. So 5. For the second member, L was 4 meters. So 4. For the third member, L was
3.
3. Yeah, correct. Fourth member, again 4. Fifth member, again 5. Very nice. So now, assembling the stiffness matrix, we see member 1 and 2. In member 1, we find where is 1, what is its value. Okay, its value is 0.64 by 5. We write it down. 0.64 by 5. Then we go to member number 2, stiffness matrix of 2. We find where is 1, and we find the value of 1 comma 1. We find it is 1. So it's 1 by 4. 0.64 by 5 plus 1 by 4. This is in the first matrix. Is it clear?
Yes.
it is clear. So let's find the second one. So if we are trying to find the element of 2 comma 1, what we have to do for 2 comma 1?
Again, same members. We have to just check the same matrix.
Same matrix we have to check. Member 2, member 1. 2 comma 1, it is 0. So what we write down here? We write down 0 plus, we find here 2 1. What is the answer? 0.48 by 5. So what we write down here? We write down 0.48 by 5. I think it is clear now. For 3 comma 1, again we have to find out where is 3, where is 1. So let us quickly go and check. 3 and 1 are connected with only one member. Only this member. Is my ink visible? Only this member, right? 3 and 1 is connected.
Yes.
Yes.
Only member 2.
Only member 2. So in that case, only member 1, I guess. Only member 1. So in that case, what is 3 comma 1? 3 here, 1 here. 3 comma 1 value is minus 0.64 by 5. 3 comma 1 value is minus 0. So like this, can we find all the different matrices, all the different elements? Is there any doubt in this?
No, sir.
If there is no doubt, then I will move forward then, like, because we have to now find all the elements. So instead of that, I will move forward. Shall
Yes,
I
sir.
move
Please.
forward?
Yeah,
Yes,
yeah,
sir.
please.
Yes. So I already have the stiffness matrix here ready for you. Let's quickly check. First one, we have to add something. Let's forget about that. The element 2 comma 1, 0.48 by 5. 0.48 by 5 is 0.096. It is fine. Okay. The third element 0.64 by 5. 0.64 by 5 is minus 0.128, minus 0.64 by 5. So it is correct. So this is how we have written all the different elements of the global stiffness matrix. This is the global stiffness matrix. Correct? Okay, very nice. So now comes the big question. What is in the left hand side? P1, P2. We are writing P or F. I think we are writing F, right? F1, F2, F3, F4, F5. This is okay till now?
Yes.
Okay, very nice. So now I have already included some of the things here as screenshots because it will be difficult for me to write it in some short place. Only the stiffness matrix is so difficult. Anyways, so now let us quickly draw the truss problem. Okay. Okay, so this is our problem. What we have is we have a hinge here, we have a roller here, we have a roller here. So now What are the degrees of freedom that is 0? Please, answers.
1, 2, 6, and 8.
1 is 0, 2 is 0, 6 is 0, 8 is 0. I hope everybody agrees. 0, 0, 0, 0. Okay. And interestingly, what we find here is that F1, F2, F6, F8, these are the unknown Fs. Right? We know the displacement here and we don't know the force here. But we already know the forces F3, F4, F5, F8. What are the forces F3, F4, F5, F8?
No, it is F5, F7.
Sorry, F5, F7. Yeah, sorry.
F5, F7
We
is
have
0. And
F5, F7 is 0, F4 is 3, and F3 is minus 3. Okay. Quickly go back to the main problem. F3 is minus 3, F4 is 3, F5 is 0, F8 is 0, F7 is 0. Fine?
yes.
Okay, very good. So we have written that down here. So, okay, they have written in terms of P1, P2. Please bear with us together. So, P1, P2, P6, P8 we don't know, but we already know P3, P4, P5 and P8. Okay. So whatever equation we have here, whatever known unknown we have just written down that same thing here. Is it acceptable?
Yes.
Okay. So now comes the main question. So now what do you want? You want it to be in the form of, say, P known, P unknown equals to K known unknown, K known known, K unknown known, K unknown unknown. Sorry. K unknown unknown, K unknown known, and U unknown, U known. You want it in this form, right? So what do you actually want? You want that all the P knowns, like all the okay, all these values they come together at the top, and all these values 0 0 0 0 they go towards the down. This is what you want, right?
Yes. Yes.
Yes. Okay. So first of all, without changing the sequence of u, keeping constant the sequence of u, we can just interchange the rows to change the sequence of p. Is that correct? Very big claim here. Is that correct?
No, in fact, that is what I wanted to know.
Yes. Okay. Let's go to the last page. I have one equation, say P1 equals to AX1 plus B, not, I don't know what notations to use. Say A equals to AX1 plus BX2 plus CX3 plus CX3 plus DX4. B equals to Just forget about it. I am using the same. Okay. A3x1 plus B3x2 plus very nice. Can we form the matrix equation for this set of four equations? A, B, C, D, x1, x2, x3, x4, A1, B1, C1, D1, A2, B2, C2, D2, A3, B3, C3, D3, A4. Okay, this is clear. So we have written down this set of equation as this. This is clear?
Yes, sir.
Yes. So if this is absolutely clear, let's interchange these equations. Let's write it in the form of B first, then A second. If we want B first and A second, what will we do? First we will write B equals to A2, B2, C2, D2, and A second means A1, B1, C1, D1. Clear?
Whether X1 and X2 will be interchanged or not.
Pardon, your voice is not clear. I am sorry.
X1 and X2 will be interchanged or not.
Probably columns also we need to interchange.
Okay, so you are so you feel that the columns are also needed to be interchanged.
I think so.
Okay, no problem. Okay, so here what we do is we write B as the first element, first row, D as the second row, A as the third row, C as the fourth row. Okay, so what we write here, B, D, A, C. Okay, and here we write x1, x2, x3, x4. Okay, so for the first case, B equals to this into x1 plus this into x2 plus, you get the point, right? So
Yes.
B is equals to how much into x1? B
A2.
is a2, a2 into x1. B equals to how much into x2?
B2.
B2. How much into x3?
C2.
C2. D2.
D2.
Okay. D equals to how much into x1?
4 A4.
Okay.
A4 B4 C4 D4. Yeah.
Okay. So do we still feel that we need to change the columns?
No.
No, right? So now it is clear, right, that we do not need to change the columns unless we are changing the this matrix, the x matrix. Unless we are changing the sequence of x, there is nothing related to that column. So we can also recall that we have one question, that what is the column in the stiffness matrix that corresponds to the second degree of freedom. So this is the, say this is the column that corresponds to the second degree of freedom. So if these sequence same remains same, the columns don't move. Okay, but if the rows move, the left side moves. Okay, this is like acceptable now. Is this clear now?
Yes.
Yes. So I hope this is clear to all now. Yes. Then I'll move forward. This is clear, right?
Yes. 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 Yes.
Yes,
Yes.
yes, yes, yes. Okay,
But
very
then you
well.
said something on the stiffness second. I didn't understand. What is that?
Okay. So
You
there
said the
was.
row is acceptable.
Mm-hmm.
Interchanging the rows is acceptable. No questions on that. But you
Yes.
mentioned something on the stiffness second degree and this. What is that?
Yes, yes, yes. So there was one question you remember, I guess, in the uh, if we quickly move to that question.
Week 2. What is the second column?
Yeah, yeah,
Second
yeah.
degree of.
In week
Okay.
two, there was one question. What is the column in the stiffness matrix that corresponds to the second degree of freedom? Okay.
Correct.
So
Correct.
then you quickly answered that it will be the second column that will correspond to the second degree of freedom.
Okay.
Okay. So the reason behind this is whenever the second degree of freedom comes into play, every time these coefficients gets multiplied with them, right? this is the this is the stiffness
Okay.
that
Got it.
is.
Got it. Got it. So it doesn't matter which one you're multiplying first or which one you're multiplying second. Okay. I got.
Yes.
Got. Agreed.
So unless you are changing the degrees of freedom, your columns will never change their position. Unless you are
Agreed.
changing the degrees of freedom sequence, your column sequence will never change. Okay. So I hope it is now clear. So moving on. So now it is acceptable that if we want to interchange the if we want the unknown if we want the known forces first, we need to interchange the rows. That is okay, right? So there they have written now interchanging the first and fifth row and second and seventh row to make the force vector p known, p unknown. Okay, this part is clear. Fine. Quick disclaimer that we may overshoot this class by 5 to 10 minutes. Is that possible, or should we end the class and discuss in the next class, whichever is acceptable to you?
I think let us close this. Grouping that, then we can solution. We can take it up in the next class. I think.
Okay, so we can do till the grouping today, like the interchanging. Then when we achieve this formula, this formula whenever we will achieve, we'll stop there and we can solve in the next class. That's what we want, right? Okay.
Yes.
So by changing the interchanging the rows, now we have all the known forces over here. Okay, and we have interchanged the rows to find the rows to, like, we have changed the stiffness matrix accordingly. Okay, so this step is clear. Now the next question is, now we want the unknown displacements first and the now we want the unknown displacements first and the unknown displacements second. Okay, so what we want to do is we want to bring u3 first, or say, okay, u3 we can, u3 is already in position. We want to bring u5 here and u7 here. Okay, so we are now trying to bring u5 in position 1, u7 in position 2. So what should happen to the stiffness matrix? Answers.
Interchange the column now.
Yeah, interchange the column now. Interchange the column now. So now interchanging the first and fifth column and second and seventh column to make the displacement vector uk uu uk. So again, should I again explain it in this context, or is that okay?
I think that should be fine. We can try that. Yes, the concept.
Okay. So through this again we are seeing, I don't have space below, so I'll just write it above. So now we have, say, we keep it the same, A B C D. We know about the rows now, we are not worried about the rows now, but we do it like x2, x4, x3, x1. Okay, so ABCD equations are known to us. Left hand side is ABCD, right hand side is x2, x4, x3, x1. So when we write the first row of the matrix, A equals to what into x2? A equals to
It is
what into x2?
A2 x2.
Now, A equals to what into x2?
A2.
Uh, B1.
Oh, sorry, B1. Sorry.
Uh,
Yep.
B1 into x2. Okay.
Yes.
Then x4. A equals to what into x4?
D1.
D1. A equals to what into x3? C1. And then A1. Similarly, B equals to what into x2? B2.
B2.
B,
Yeah.
B equals to what into x4? D2.
D2.
Then C2, A2. Similarly, if we
Okay.
see, we find B3, D3,
B3, D3, C3.
C3,
Okay.
A3, and B4, D4, C4, A4. Okay. So if we just interchange the if we just interchange the like elements of the displacement vector, we have to interchange the columns. Okay, so this is the underlying concept behind it, like why it is happening like this. So this is clear. I hope this is
Yes.
clear. Yes,
Yes.
yes. So now just interchanging the first and fifth column and the second and fourth column, we will get the form of, they have written u unknown and u known. That is what the form we wanted, u unknown, u known. So after doing this, so now you see what is this in the form. So let me write down, this is actually k known unknown, k known known, k unknown unknown, k unknown known. This is u unknown, u known. This is p known, p unknown. Now we have actually got this form.
What happens to this
Mhm.
changed global stiffness matrix? That property still remains same as
Changed
the
changed global stiffness matrix, the properties as in the yes, property still remains the same, uh, only the
still it will
degrees
be
of
singular. Still it will be again singular, that
uh,
matrix after
s-
changing.
still it will be singular if we like don't impose these
That's okay.
what to say.
I'm not coming to that.
Hmm, hmm.
Boundary conditions. So before, if I don't apply that,
Uh-huh.
is that
Yes.
matrix again okay?
This matrix again, it will be like singular, this matrix itself. There will be no difference in this. But then the smaller matrices, those will not be singular anymore.
That's okay.
Okay.
That's fine.
Yeah.
That is understandable. That
Yes.
makes me understand.
Yes. Okay. So this is what. So now we have the equation pk pu equals to kku kkk kuu k. I guess you can understand how I am writing this u and k different times.
Yes.
Yes. Just to explain to the class that this k relates to this one, u relates to this one, and this u relates to this one, u relates to this one, k relates to this one. Okay. So the first k is for the force vector, second is for the displacement vector. So why it is like this? Because now this is, say, a 2 cross 2 matrix. Say this is 2 cross 2, this is 2 cross 1, this is 2 cross 1. So we can write the equation of motion from this, right? Say equation of the system from this, right? So k k u into u u plus k k k into uk. Then pu equals to k u u into u u plus k uk into uk. This is fine. This equation, this is fine, right?
Yes, yes, yes.
So now uk is 0, as we remember. All the known displacements are 0. So now we can solve the problem by these two equations. Okay. So now we
Okay.
know pk equals to k ku uu, and then we can easily find uu equals to what? We know the stiffness p known and the k ku. Okay. So this is how we solve the problem. You can also like solve the problem by your own. I think now there is no need. But then in the next class, what we do is, in the next class we continue with what is the solution of this, and then how to find the element forces from there. Okay.
One small addition, Mr.
Yes.
Manager. What in the
Yeah.
next class?
Yes. Yes.
This trust problem. Okay, it is a straightforward. PK is equal to KK and UK. That we'll get
Okay.
that.
Hmm.
But in when it goes to beam problem,
Hmm.
it is something again. It is different
Okay. So in that
because there
case, yeah.
will not directly get the, because here we'll directly get that forces. There we don't get the direct unknown reactions, but we need to add it to that fixed end moment, and then we need
Yes.
to that. So why? I mean, what
Yes.
is that logic there? Why it is different?
Yes. So I am
It is
happy
not
to.
straightforward like this. Beam element is not straightforward, but there
Yeah.
we are telling unknown displacement. We directly get it in one step with this unknown matrix or whatever is that. But to
Yes.
solve that forces, again we need to add to that beam and what is that? Equivalent joint forces, and then we have to get the reactions.
Mm-hmm.
So that cycle something confusing there.
Okay. So so the like good news is that the next week I think we have the beam problem. I think I
Yes,
have not seen the lectures for this week. Have you seen?
it's already there. It's already there.
It's the like beam stiffness matrix, right?
Yes, yes.
Mm-hmm. So we can discuss that in the next class in detail.
Sure, sure, sure.
Yeah. Again, I guess I'm not sure. I have not checked the assignment for the next week. But again, I guess there will be something similar like this one big beam problem, and then we'll solve that maybe. So in that, a lot of questions would be answered, I guess.
Fine, Mr. Ganesh. Yeah.
Yeah.
Good.
Okay. So the class we can end it here, and we can resume from this unknown matrix, unknown solution from the next class. And apart from that, there was some discussion that Mr. Sudhakaran wanted to have with me, so we can continue with that discussion.
Okay,
Miss,
fine, Mr. Ganesh. I'll log off.
yeah, yeah,
Thanks
yeah,
for the.
you,
Okay.
yeah, yeah,
Good night. Bye.
yeah. Good night. Hello. Uh, Hello. Your voice is very weak, I would say. Yes, yes, your voice is audible, but it is not absolutely clear. We can manage. You please go ahead. Uh, oh, you are right now traveling. Okay, okay. So it is fine with me if you want to talk at some other time instant. No problem for me.
can you mail my idea to your, can I mail you
Yeah, yeah,
my
please,
idea?
please email me. Yeah, please email me. I hope you know my email ID.
Yes, sir. I'll take that screenshot.
Okay.
Right.
Uh, I would once again write the email ID here in the in this document. So what I will upload this document also. You can check the email ID from here, and also um, you can download this document to find my email ID. This is fine. So we can talk through email, right?
Yeah, yeah, sir.
Okay.
I will send it to you.
Okay. So shall we end this meeting here?
Yes, sir. Enter-
Okay.
Enterprise.
Okay. Okay. Thank you very much. Thank you very much. Yeah. Good night.